In this video, we are going to be looking at the structure and bonding found within alkenes. Now, alkenes, as we know, is another functional group, and the two words that we can describe alkenes with are unsaturated and hydrocarbon. So we can class alkenes as being unsaturated hydrocarbons. Unsaturated means that there is at least one double bond present. So by a double bond, I mean between two carbons, there is a double bond. Okay, so for a molecule to be unsaturated or to be classed as an alkene, it must have at least one double bond in the molecule. Hydrocarbon just means that it has, it's made up of atoms of carbon and hydrogen only. We're now going to have a look at the alkene homologous series. So the first member of the alkene homologous series, it's not just one carbon, because obviously to have a double bond you need to have at least a minimum of two carbons. Okay, so the first member of the alkene homologous series has two carbons, and that's this molecule over here. So this molecule is called ethene. Okay, and as you can see, the molecular formula for this is C2H4. Okay, bearing in mind, so whenever you draw any organic compound, carbon must form 4 bonds. So over here it's got 1, 2, 3, 4. Same thing with over here, and you'll see that in all the molecules that I draw, carbon must form 4 bonds. And make sure when you're drawing them as well that you double check your carbons have formed 4 bonds. Okay, so this is the first member of the alkene homologous series. The next one is this one. I'm not going to show all the bonds in that CH3 group there, but again, one double bond, and it's now got 3 carbons in it, so it's going to be propene, and the molecular formula for this is C3H6. In terms of naming these, I will go over naming them in a different video, but as you can see, alkenes end in -ene. Okay, so if it ends in -ene, that tells you it's the alkene functional group, it has a double bond in it. The prefix at the beginning tells us how many carbon atoms are in them, so eth for 2, prop for 3, and so on. Okay, if we look at the molecular formula, hopefully you can see that the general formula for these is Cn, and the number of hydrogens is double the number of carbons, so it's CnH2n. So this here is the general formula for alkenes. I'm also just going to show you what this molecule would look like in skeletal form. So if we're showing 2 carbons bonded to each other like that, but there's a double bond, so I'm going to show 2 lines. So there's carbon at each end and there's a double bond between them. This one over here, again, we've got our carbon double bond between 2 carbons, and over here we have a CH3 group coming off. So that's how I draw the skeletal formula for propene. Also, pointing out the fact that they're part of the same homologous series, as we go from one member to the next member, so the successive member, we are adding a CH2 unit to the molecule. So that means that they're part of the same homologous series because they have the same functional group, and each successive member adds on a CH2 unit. Okay. Again, also worth pointing out that this general formula here only applies to alkenes with 1 double bond in them. So if you have a straight chain alkene or a branched alkene, this general formula applies. But if you have an aliphatic alkene that has more than 1 double bond, this general formula doesn't apply. Also, if you have a cyclic alkene, so for example, this alkene over here, because it's cyclic, it's alicyclic, it doesn't fit the general formula here. Okay, right, let's now go on to look at the bonding in alkenes. When we were looking at alkanes, we covered a term called sigma bonds. So single bonds are classed as sigma bonds. So within an alkene molecule, you will also have sigma bonds. So there's sigma bonds between the carbons and the hydrogens, and there are sigma bonds between the carbons and the carbons. Okay, so let's just cover the sigma bonds first. So I'm going to do a molecule of ethene, just because it's the simplest alkene. Okay, so at the moment, we only have sigma bonds drawn here. Okay, so between the carbon and the carbon here, there's a sigma bond. Between all the carbons and the hydrogens, there are also sigma bonds. So these over here are called sigma bonds, like that. Okay. And remember what I said, so carbon must form 4 bonds. The reason for that is that carbon, is in group 4, it wants to gain 4 electrons, and it does that by sharing its 4 electrons. At the moment, each carbon has only formed 3 bonds. Okay, so it's formed 1 here, and 1 here. So that means only 3 of its electrons are involved in bonding. There's still 1 electron that's not involved in bonding. That 1 electron is found in a p orbital. So if you remember, p orbitals are this shape. So this is 1 p orbital. That, that extra electron is in this p orbital somewhere. Okay, and the same thing happens. I'm just going to rub this out to make this diagram slightly clearer. The same thing happens with this carbon over here. There is a p orbital with that electron in it. Okay, so we have 3 electrons involved in bonding, and 1 electron is found in this p orbital, and the same thing applies to that carbon as well. I've got a little model here to show you, just so you can see what that looks like. So this is our ethene molecule. Okay, so we've got our carbon bonded to 2 hydrogens and the other carbon. So all of these grey bonds here are sigma bonds, and if I just turn the molecule over like that, so all of these atoms are now in the same plane. Okay, and the p orbitals are technically perpendicular to that plane. Okay, so these p orbitals contain an electron. So this one contains 1 electron, this one here contains 1 electron as well. These p orbitals are going to overlap sideways. So I'm just going to write that underneath because it's an important phrase to know. So the p orbitals overlap sideways. And this is the phrase that you'd have to use in the exam to show, this bond being formed. So the p orbitals overlap sideways. So I'm just going to show that by overlapping it with a line. And when they overlap, they form this. Okay, so when they overlap, they form this. So this is an area of electron density above and below the plane of the atoms. Okay, so going back to this model over here, this will overlap with that, this will overlap with that, and that forms what we call a pi bond. So this over here is a pi bond. So both of these are 1 pi bond. Okay, so there's only 1 pi bond that I've drawn here. So p orbitals overlap sideways to form this pi bond, and that's what we call that double bond. Okay, so this, between the carbon, we have a sigma bond. So this was the sigma bond here. And above and below the plane of the atoms, we have a pi bond. Okay, so in an exam, if you wanted to draw that, you could draw out this diagram here where you've got the p orbitals overlapping sideways from the overlap over here. So these red lines over here are showing the overlap of the p orbitals sideways, and this over here is showing the pi bond being formed. Okay, so that's what we call the double bond forming. Okay, a double bond is actually a sigma bond and a pi bond, and a pi bond is found above and below the plane of the atoms. And what that does, or what the formation of a pi bond does, is it means, so over here I've just got my ethene molecule. Okay, it's got the double bond between it. So that double bond here is technically a pi bond and a sigma bond. Okay, obviously that's not depicted properly over here, but that is essentially what a double bond is. Because we have a double bond now between these two carbons, it means I can't rotate it. Okay, they're stuck in that, they're in a fixed position. So in alkene molecules, or in, with double bonds, there's what we call restricted rotation. Okay, I can't rotate this molecule. Okay, it's stuck in that way. So there is restricted rotation. So there's restricted rotation around the double bond. Okay, in terms of shape, so if we look at the shape of the molecule, this over here, so the double bond is one bonding region. Okay, so we class it as one bonding pair in terms of electron repulsion. So each carbon has 1, 2, 3 bonding regions. These bonding regions, or these bond pairs, want to be as far away from each other as possible. So in order to do that, they adopt the trigonal planar shape. So in a double bond, in any double bond, the carbons in that have a trigonal planar shape. Okay, and between each of these bonds, there's a bond angle of 120 degrees. Okay, and that applies to any double bond involving carbons. We have a trigonal planar shape, and the bond angle is 120.